honest. And so that's where things are relative to each other in the actual photo in reality. So my...
Look, now he calls that matching reality right there. Look at the little tower to the left. It's going to the top of the mountain. He's calling that halfway or whatever. It's a little more than the top, or at least level with the top. So for him and his model to line up Blackpool with Dow Craig, okay, nothing else matches. Okay, look how he's got them little towers to the right, halfway up the mountains, but he's got the mountains going down to the water. Okay, now you tell me if that matches. Now you see the little towers to the right? Now if you go all the way down to the water, it doesn't work, okay? He's trying to scale everything the same, no matter how far away it is, but it doesn't work in his model. Look at the little tower to the left. That's not going to the top of the mountain. I mean, is it? No, it's not. But obviously refraction is very important. So I request they start using our refraction, okay, in their model, which is standard horizontal refraction, meaning a horizontal viewing angle. That's light refracting upwards at a rate of about 5 inches per mile squared, okay, making objects in the distance appear lower at a compounding rate, basically. So, and one more thing. Watch what they do with the flat Earth model here. This is his idea of a flat Earth model. Okay, so what they have is the mountains going up higher, and in their model, anything, so something further off in the distance, but even higher, would keep going up in the picture. So there would be no convergence. Like, say, picture a target from an auto level, a crosshair. Everything converges from the top down. They go by strictly trigonometry, and then they include the refraction. But on a flat Earth model, they would have everything just getting higher and higher and higher, and not converging toward the middle. So that's a poor depiction of a flat Earth model. If you ask me, it's not honest. That's my opinion. But refraction is very, very important to them. I'm going to point that out before I get to my point in this video.
Refraction. So I'm using 7/6R refraction, standard refraction here. And that allowed me to build a little triangle. I've kept it all in kilometers. Right, so this is the height I got, which is actually smaller than the mountain should be. Sort of orange squares where you stick in your inputs. So again, I'm using standard refraction, 7/6R, you see up here.
Okay, these are the distances and heights we ran the numbers on. You have for the mountains that are 81.5 kilometers, we transferred that to 51.64 miles. So 770 meters height converts to 2,526 feet. Okay, so 51.64 times 51.64 times 5 inches, okay, divided by 12 to put it back in feet is 1,111 feet. That gives us our new refracted number to put in the calculator of 1,415 feet. Okay, now for Blackpool Tower, 180 meters in height. Okay, so we got 12.19 miles times 12.19 times 5 divided by 12 to put it back in feet is roughly 62 feet. So that gives us a new height of 528.5 feet to put in the calculator. So let's see what we get with these refracted values. So we're going to put our new numbers into the triangle calculator. And for anybody who hasn't used this, it's pretty easy. You look at the triangle, okay? You have sides A, B, and C, okay? A always, well, first off, the A in the bottom right-hand corner, that cursive-looking squiggly A, that always represents the viewer. So if you want to apply this, that point right there down at the bottom right is the viewer. B is the distance, and you always want to convert it to feet, okay? So whatever miles it is, you convert that into feet by multiplying it by times 5,280. And A is the viewer height. and you put that in feet. So whatever scale you use, just make sure it's the same. Don't try and mix miles with meters or feet or kilometers. You know what I'm saying? But they make it sound like this, like they're heavenly gods because they've brushed up on their trigonometry, or they do it for a living. They're not. They're knuckleheads. Okay. But for anybody, that's just for anybody who hasn't used it, or hadn't brushed up on their trig in a while, or hadn't used the calculator. Simple shit. They're full of shit. Trigonometry is nothing special. Okay. You can teach that. You can't teach common sense. Okay, people. Okay. So our new refracted values. Okay, so B, okay, A, the height of the mountain, the new height is 1,415 feet. That's our refracted value. And then B is the distance. It's 51.64 miles. That's times 5,280. That comes out to 272,659. Okay. Calculate. Okay, that gives us 0.297 degrees. I'm going to write that down. You can't see it, but 0.297 degrees. Just remember like 0.3, just about. Okay, now we're going to do Blackpool Tower. The new height is 528.5 feet. Say B, that's the, wait, that needs to go where A is. Excuse me. Well, since we're at B, we'll do the distance. So this is 12.19 miles times 5,280. That equals 64,363 feet. And A, the refracted height is 528.5. Okay. So our angle to that, what do you know? What do you know? It's 0.47, almost 2 degrees higher. So Blackpool has a bigger angular size than the mountains. And what do you know? You look at the photo, and that's what you get. So they don't like to they like to add in their refraction. They don't like to talk about actual real life refraction, do they, folks? They like to try and put themselves up on a pedestal as gods because they're brushed up on their trigonometry. It's a fucking joke, man. Here's another trick they like to pull that I want to point out. So if they use A, the Blackpool height of 180 meters, okay, and the distance would be B, would be 19.62, so 19,620 meters, or 19.62 kilometers. So you get the angle A, viewers, or they call angular size, of 0.526. Okay? Now, if we subtract the 12 meters that Reggie uses and call it 168, we subtract that, then we get an angle of 0.491. So now, let's see what 0.491 angle does with the distance of the mountains. So 0.491. So 0.491 at a distance of 81,500 meters gives us 698 meters in height. Okay, remember 698. Got that written down here, but you can't see it. But 698 would be the exact mountain height without refraction to line up with Blackpool Tower. So then we use the one before they subtracted the viewer height, which was 0.526. Okay, remember? So 0.526, and we get 748. Okay, so instead of 12 meters now, That's another almost 40 meters. So they like to just subtract the viewer height and equal it out the same at Blackpool as they do the mountain, which is deception. Okay, I don't know if they're ignorant and don't know how to do the trig, or if they're lying through their teeth. But it's not honesty. Okay, they you know, go through our shit, scrutinize all of our numbers, all our math, but that's almost 40 meters different, and they only count it for 12. But the fact of the matter is, we know that off in the distance, okay, objects, whatever it may be, a mountain, whatever, is going to move lower. If we drop our viewer height lower to the ground, it's not going to move like objects in the foreground. It's the objects in the foreground are going to contrast way more than the objects in the background. It's common sense, it's perspective, and they've been lacking that lately. But I want to try and keep it on check. They like to include refraction, so they need to include our refraction.